ITMO is quite a famous institution, so I'm very pleased and delighted to give a talk at this department seminar. Well, perhaps the title of my presentation is a bit unusual for this seminar because it has nothing to do with microwaves, and it's mostly a very different area of underwater acoustics. Well, I'll try to start with the basics. I'll try not to be too much boring, and hopefully, well, some parts of the talk will be a little bit entertaining for the listeners. And yes, as Dmitry already pointed out, you can ask the questions during the talk. I'm quite happy with that. Well, let me begin. So, let me first start with an extended introduction of myself. So I would like to extend introduction of myself to my institution, the POI. Well, it's Pacific Oceanological Institute, and it's located in Vladivostok, and you can see here our building, which is located more or less by the sea. And here is the founder of our institute, academician Ilyichov, yeah, it's our namesake. It's quite a large institute, and we have about 400 employers, and among them 200 scientists, and we conduct complex research of everything related to the ocean. So ocean chemistry, ocean geology, ocean acoustics, ocean everything, more or less. So, well, I think it's one of leading Russian institutions conducting studies of the ocean. So, well, if you want to show people that you are from Vladivostok, you normally show a picture of our bridge and the numerous vessels below the bridge. And this is Golden Horn Bay, the main bay of Vladivostok. And in this bay, it is in this bay where our scientific fleet is stationed, and you can see two examples of our research vessels, which are operated by POI. This is academician Nismiyanov, and this is one of our main workhorses, research vessel academician Lavrentiev. So we more or less conduct seagoing programs annually, every year, several times. Scientists from our institution go to sea on this beautiful vessel and do a lot of things. So it's relatively large for a research vessel, and there are not so many research vessels of this size in the world. Sometimes we even conduct some measurements from tall ships like this one, this beautiful frigate. And even we do some research using yacht. Like this is our institution's yacht, which is mostly used for underwater acoustics. Well, let me also briefly discuss what underwater acoustics is all about and what we actually do in underwater acoustics. Well, underwater acoustics is mostly wave propagation, compressional wave propagation or acoustic or sound wave propagation in the marine environment. So mostly in the seawater, but sometimes we have to include also bottom, and sometimes we want also to include air, but not very often. Mostly it's propagation of sound in the water. So one might wonder what is so complicated about it. So it's more or less described by well-known equations, and it should be really relatively easy. So not so many new physics you can expect to find in this area. But actually there are some issues which are difficult to handle even now, because well, our problem is the scale. So we deal with the areas of huge size. So, I'll go into details in my talk. Well, I would like to show you a few examples of acoustic equipment. So here you can see acoustic transducers. So we have relatively large ones like these two. These two guys, they are deployed from a ship using a deck crane. You can't lift this manually. It's very large and very heavy, few tons. And it's a piezoceramic transducer. So you can generate some signals and emit them and then receive them elsewhere. And then you can study how the sound propagates. So, for example, this one is used to transmit navigation signals. This one is much smaller. Well, it's driven by car pump, and you can just pump some air inside, and at some point it makes a clap. So produce a pulse, sound pulse. Well, it's much smaller, but still can be very useful. Take a look here. It's me and a transducer, this one, very large one, you see. But this is not as large as on the previous slide, but still its weight is about a few hundred kilograms. And here you can see the typical receiver which is used in acoustics. This is a hydrophone. The hydrophone is basically the same as a microphone, but it's used to record sound in the water. So it's mostly based also on piezoceramic. And so this is basically a reference hydrophone for this transducer. So when we transmit sound, we want to have some reference measurement near the transducer. So you see it's placed. When you deploy the transducer, you can, you have some reference hydrophone here. Okay. Well, I just can't stop myself from showing you this slide. This is actually also a kind of transducer. This is a sperm whale, right? The largest animal on the earth. And basically, a sperm whale is a giant acoustics transducer. Because if you look at this scheme, you can see that the skull is here, and here it looks like there is some empty room in the nose of this animal. But actually it's filled by some kind of fat tissue. It's spermacet and melon. And actually this is a huge acoustic transducer. So you see here frontal sac. This wall is covered by some small bubbles filled with air. So it works like an acoustic mirror. And this is like a huge beamformer. And actually all this nose, which has immense weight, is used by this animal to transduce the sound and then to receive the sound and to to navigate in the marine environment and also to communicate with other animals of this species. And they can transmit and receive these signals quite from afar, so like half of an ocean actually. So well, the same is about most of species of whales and dolphins. They all have some internal integrated acoustics transducer. So this is a very exciting area of bioacoustics, which is also like part of ocean acoustics. Well, let me go briefly into the history of underwater acoustics. So you see the first application when people realize that underwater acoustics is actually useful and even necessary is a sonar. And you see the first experiments took place in 1915, and you can easily understand that it's related to the First World War. And the necessity was to detect German submarines, of course, and because they made immense impact on the course of the war. And it's at this time when German declared unrestricted submarine warfare. And they basically started to think all allied ships, like no matter merchant ships, cargo ships, or military ships. So it was like a key point to secure victory. The key point was to develop the way to detect these submarines. And the first prototype of what is now called sonar, which is an abbreviation for sound navigation and dredging, was created by French physicist Paul Langevin and Russian engineer Konstantin Shilovsky. You can see the pictures of these people here. So it was actually the first real application of underwater acoustics. And yes, it was military. And since that time, actually, huge branch of underwater acoustics is classified, military, and mostly somehow related to submarines. But what we do has nothing to do with that, so I can give us this open presentation, so don't worry, no classified information comes here. Well, and let me outline the most important areas of applications of underwater acoustics. So as I already pointed out, there are military applications, which is mostly submarine detection and cloaking. I mean, cloaking is also like a very hot topic. So like to design a coating which can be used like a cloak for submarine to hide submarine, to conceal it, so that enemy can detect it by his sonar. Well, another area is what is called waterside security, which is mostly related to diver detection. So like if you have some some facility operating on the seaside and you want to protect it from invasion from the sea, you want to probably deploy some means for diver detection and somehow ensure this waterside security. Another hot topic is nuclear test ban treaty monitoring, because most of the time, nuclear tests are conducted on small islands, on atolls in the sea. And actually, you can easily detect this test by acoustic means. So you can do monitoring by, let's say, deploying 10 or 20 stations around the globe. And because sound propagates very large distances in the underwater sound channel, you can detect these nuclear explosions from afar, from like thousands of kilometers. You can do it easily. So it's more or less natural way to do this monitoring. But also what is like, I would say, gaining prominence in recent years. So now underwater acoustics is mostly about non-military applications. And let me mention a few of them. Well, I would say these ones are the most like acoustic noise monitoring and environmental impact assessment of acoustic noise. So what is it all about? It's like when you conduct some noisy activities in a marine area, you might wonder if it makes some impact on marine fauna, like on marine mammals, on other animals, and you want to estimate the impact of sound and you want to protect these animals. Well, so you need to do acoustic monitoring. This is one of the most important things, which are, for example, one of the most important practical applications in our institution. So our institution, well, not my lab, but another lab is conducting this acoustic noise monitoring on the Sakhalin shelf, where they develop hydrocarbons like oil and gas, and they construct some facilities for, they do seismic survey, and so you need to do acoustic monitoring. You need to find out how much this is dangerous for the animals. And in particular, on Sakhalin shelf, there is a like population of gray whales. And many companies, all companies which are operating these oil and gas facilities, they have to estimate the impact of their activities onto these whales and to check if it's not dangerous for whales. Well, another very important topic is underwater navigation and ranging. So sometimes you want to navigate in the sea, but you don't want to surface. For example, if you operate some small autonomous underwater vehicle or underwater robot, and you don't want to surface every time when you want to update your coordinates, then you need acoustic means for do navigation, like underwater GPS, if you like it this way, because you can't use normal, of course you can't use normal GPS under the surface, because radio waves do not penetrate into the sea, into the water layer. So you need acoustic. The only thing you can use is acoustic tools of navigation. This is another very important topic for our institution, as we are currently conducting a huge research project dedicated to development of acoustic navigation systems. The next thing is acoustic sensing and geoacoustic inversion techniques. Also, you might like to include here acoustic tomography. So you want to get some information about the marine environment, about temperatures, current speeds, and other things. And you can do it actually by acoustical tools. You can transmit somewhere, receive elsewhere, and you can get the information about the medium where the sound propagates from this measurement, from the from the waveform of the received signal, or from its frequency content, or from its modal content. So you can get a lot of information from this in this way. Another important thing is bioacoustics. I also mentioned that, well, acoustics is the main tool for, well, for navigation and for communication of marine mammals like whales, dolphins, orcas. Well, and this is very exciting topic because they actually can communicate, they transmit a lot of information by acoustic tools, and you can actually distinguish navigation signals and communication signals. And this is really interesting because you might heard the so-called whale songs because it's really beautiful when orcas sing under the sea. And this is actually their way of communications, like they're more or less they are speaking to each other. Well, this is, and of course, this kind of speech that can cover large distances, and the orcas can hear each other from, let's say, tens or even hundreds of kilometers under certain conditions. Well, now I would like to turn to more, let's say, to be close to the title of my topic. And I would like to explain why measurements are not enough, and we often need to have a good way of simulation of acoustic wave propagation in the sea. So why do we need simulation, and what are the main challenges here? Well, let's say, well, again, it's here military applications. This is not, well, there should be purposes. Well, for example, if we would like to predict noise levels and assess its impact onto the marine fauna, and we want to have noise levels over some large area, let's say tens of kilometers by tens of kilometers, which is huge. And of course, you can't cover all this area by receivers, by hydrophones, because hydrophones are very costly. And the deployment of hydrophones is even more costly than hydrophones themselves, because you need to operate some vessel. Vessels is they are normally very expensive. And so you normally want to have few point of measurements, and then using this information obtained in few points of measurements, you want to somehow extrapolate this information about the noise onto the entire area of interest. In order to do that, you need, of course, to perform some simulation of acoustic waves. And you need some good math to do this, because the area is so huge. So it can be, in some applications like noise, it can be tens of kilometers by tens of kilometers. In other applications like long-range navigation, it can be hundreds of kilometers by hundreds of kilometers. Just imagine. And even if you operate some, let's say, medium frequency range like 400 hertz, and the sound speed in the sea water is about 1.5 kilometers per second. So you can actually have like a wavelength of about 3 to 4 meters in this range, yeah. And you have the area of the size of tens or even hundreds of kilometers. So it's huge. And also it's three-dimensional, of course. And also you would like to have, sometimes you need to predict arrival times and or effective propagation velocities, because the environment is so complicated. So the water layer contains a lot of features like ADs, vortices, thermocline, internal waves, many things. And also see bottom. It's you have bottom relief, bathymetry. You so you have several bottom layers, and you have to take all this stuff into account if you would like to obtain some accurate estimation of noise levels or arrival times or effective velocities. So this is really important, and you really need some good math to do that. So it's more challenging on the side of math rather than on the side of physics, because physics is more or less, well, you can find some effects, but it's more or less well-known theories like normal theory of sound, which was, you know, more or less well established at the time of Rayleigh, for example. But on the side of math, it poses you an immense challenge because you need to do simulation in a very large area. You also sometimes, okay, if you want to do acoustic navigation, you want to put a beacon somewhere and another beacon elsewhere and the third beacon, and then do something like underwater GPS. Well, you can actually have some shadow zones. You can have pretty large zones which are not insonified by these beacons, and there you can do navigation. So you really want to predict where these shadow zones will be located and how to cover entire area, how to insonify it by a sufficient number of beacons in order to perform this navigation in a proper way. Well, and sometimes you want to do geoacoustic inversion or acoustic tomography. And normally, in order to do tomography, in order to solve inverse problem, you need to do numerous solution of direct problems. So you really want to perform the solution of direct problem very quickly. This is very important. Well, so we also have some other challenges. Well, I already pointed out that the domain is quite large, but and also that the media are complicated, and also, well, sometimes we lack the information on the medium. Like we don't know exactly what are the layers of the bottom. We don't know like the position of some large stones in the bottom. You never know exactly the bottom relief with very high detalization. You never know internal waves because marine environment is like in constant changes. Like it's a river, Heraclitus. You can't, well, step into the same river twice. Yeah, so the same is true about the sea. So sea is, well, it's a constantly changing. It's so variable. So you never have accurate 100% accurate information. This is like very specific for underwater acoustics. Well, let me go further. Well, so here I present an example for, well, of simulations we made for our friends from the lab who are, well, concerned about this acoustic monitoring. So you can see here the schematic of the area. So you for example, they have a seismic vessel which is doing seismic surveys. So they produce very powerful sound pulses, and they want to have an estimate of noise levels all over this huge area. Yeah, so you have bottom relief here. Here you have coastline, and they have only in these areas they have only two receivers, which are located here and here. And from the information obtained by these two receivers, they actually want to have the distribution of noise levels over the entire area. So they might have something like these pulses recorded on these hydrophones, and they want to estimate sound exposure level, which is basically an integral over the time of an acoustic pulse of the acoustic pressure squared. And so they want to compute it over the entire area. So they want to, normally we do it like this. We separate the pulse into many frequencies, and for each frequency we do the simulation of acoustic field. And from these, from the nearest hydrophone, we reconstruct the signal produced by the source. And then we do the computations and we compute the field in the entire area of interest. So this is actually, it's a huge amount of calculations, believe me, my friends. And later I will tell you how to do this more or less efficiently. Another example is related to this propagation of signals from a beacon of navigation signals. So, for example, here we have a beacon which is established near the coast, which is quite convenient to maintain. And then you, for example, want to receive this signal at this point and you want to do ranging. In order to do ranging, what you need is to know propagation velocity, some effective propagation velocity. And this is like just to show you what is the level of complexity. This is a vertical cross section, vertical cut plane of marine environment. So here we have bathymetry. So this is bottom relief along this propagation path. And the contour plot shows the sound speed. So near the surface, the sound speed, well, this is for summer. The sound speed is higher because the temperature is higher, because this upper level is heated by the sun. And near the bottom, well, the temperature is much lower. So that's why the sound speed is lower. And we call this situation as thermocline. And we want to know how the sound propagates in such environment. And just let me show you. Well, this is also vertical cut plane of acoustic field. You see, acoustic field is pressed towards the bottom by this thermocline, by this gradient in sound speed in the water column. So it more or less creeps near the bottom. And it does not insanify upper layer of the sea, of the upper part of the water column. It creeps along the bottom. And so you see, well, a lot of interesting features in this field. But this is not, well, it might look like it's two-dimensional, but it's not. Actually, well, the sound does not propagate along the geodesic line connecting the source and the receiver. It also, well, has deviations from the geodesic line. This effect is called horizontal refraction. Due to this horizontal refraction, well, you always, well, the sound always travels slightly more than the length of geodesic line. Well, for example, here, it's just, let's say, the geodesic line, the length of geodesic line is about, let's say, 136 kilometers. It's a huge distance, right? And you see that, well, these propagation paths, which are, well, I can explain a bit later why there are several of them, but believe me, it's just several components of the transmitted signal. They travel along different paths, and they can deviate from this geodesic line by a few hundred meters. It might sound like it's kind of very small deviation, few hundred meters for a path of, let's say, 100 something kilometers. But actually, it's very important if you want to perform accurate ranging, if you want to position your underwater vehicle and obtain its coordinates with substantial accuracy. So it's very important, actually. And you have to take these effects into account, this 3D nature of sound propagation, this horizontal refraction. Otherwise, you desperately lose all accuracy of your ranging and navigation. Well, so at last, I would like to go to the math, well, which is, I didn't want to actually to fill all my talk with math, although math is what we are primarily doing in our lab, because we, well, when people do some practical things, they normally address us if they want to compute something in reasonably fast and reasonably with sufficient accuracy, and they ask what we can do and what kind of math we can offer to do this computation. Well, and in this part of the talk, I'll show you our, let's say, in my opinion, this is the most promising tool of underwater acoustics. I'll briefly explain what are the options when you want to compute sound fields in marine environment, and I'll explain why what we are developing for me is the most promising and well, the most efficient way to compute acoustic fields. So if you look on the internet and try or in the literature and find what are the options for the modeling of sound propagation in this in marine environment, you find the following let's say groups of methods. Well, finite differences and finite elements. Well, as a rule, this method is hopelessly slow because, well, the size of the mesh size is as you probably know, is connected to the wavelengths. And so it's so restrictive, and you can do the computations in these huge domains. You can do the computations in reasonable time. So it's more or less hopeless. You can't expect, well, finite differences of finite elements perform with a practical speed. More or less no way. Well, another group of methods is ray theory and Gaussian beams. Well, what you know about, we probably know about ray theory and Gaussian beams, that they are very efficient. And indeed, this is the most efficient tool for wave propagation, more or less in every area where you have waves. But you see, the environment is very complicated. So, and you, in order to compute the signal in the receiver, you normally want to have eigenrays. So you want to shoot the ray in such a way from the source that it strikes the receiver. And now just realize you want to choose the ray angle in such a way that that the ray in this 3D complicated environment, after numerous reflection from surface, from bottom, after refraction inside the water column, so that it hits the receiver. This is almost impossible. Believe me, it's a very difficult problem. So whenever you want to do, whenever you go for ray theory in underwater acoustics, you end up with a code which is very difficult to adjust to every situation because the rays are so unstable. So small variation in bathymetry, in hydrology, in water column, and your eigenrays are no longer eigenrays. So it's very difficult to, well, I have a question, but whether we can compare the calculation results with the measurement results. Indeed, we can, and we normally do. But if you want to compare the waveform of received signal, this is more or less hopeless. So you never get any coincidence because the waveforms is so sensitive. But what you need to compare are some integral characteristics like arrival time, the signal dispersion, dispersion of every model component of the signal. And we perform, of course, we perform comparison. And this is the ultimate goal of any, well, application in underwater acoustics. If you don't do comparison, so you are more or less doing nonsense. So yes, we do comparisons, and I can, well, after the talk, I can go into more details. So what is another thing is parabolic equations. So parabolic equations is some, well, it's some trade-off between accuracy and efficiency. So you forget about some part of physics which is unnecessary, irrelevant in underwater acoustics, and you concentrate on what you actually need, and then you obtain something which is much faster than finite differences and finite elements, because you discretize not Helmholtz equation, which is more or less basic model for sound propagation, but you discretize parabolic equations, and you can allow much larger steps in range, and you get a much more efficient code. At the same time, they are much more reliable than ray theory of Gaussian beams. So, but still, even though it's much more efficient than finite differences of finite elements as applied directly to Helmholtz equation, it's still not efficient enough. I'll show you some example and explain what is the scale of the problem. Well, so what we do in our lab is the so-called mode parabolic equation. So mathematically, from the mathematical point of view, this is just a model order reduction as compared to normal parabolic equations. And so you get an advantage by a factor of, let's say, 10 in vertical dimension. And so you get much more efficient way to compute the field. And you can allow even larger steps in range. Well, in order to do that, you need to make few approximations, of course. So the main things the main approximations we normally make is a one-way propagation, so no backscattering in one coordinate, in the let's say longitudinal coordinate, but actually it's irrelevant because it's like few, let's say 0 point something percent the backscattering, so you can really neglect it in practical problems. And also, we normally make a diabatic approximation. Well, this is kind of a bit surprising, but it's, well, in our works, we have shown that it actually, in many cases, it works quite well. So you can more or less rely on a diabatic approximation. So actually, the trick is whenever you stay in shallow water, if you consider only propagation only in shallow water and you don't go, to the part of the sea where the depth from, let's say, few tens of meters becomes like few kilometers. If you don't cross this line, then a diabatic approximation works quite well. The only thing where it doesn't work is when you cross from shallow water to deep water. Then a diabatic approximation is no longer valid. But if you stay in shallow water, it's probably okay for you. And let's say, show some history of this theory of mode parabolic equations. So narrow angle mode parabolic equations were first proposed by Mike Collins in his 1993 JASA paper. JASA, Journal of Acoustical Society of America, the main journal on acoustics. Well, they were independently derived by Mikhail Trofimov on the using multiple scales, so it's slightly different derivations, slightly different equation, but well, a few years ago we have shown that they are equivalent actually in our acoustical physics journal. Well, and then a few years ago, we started to develop what we call wide angle mode parabolic equation and pseudo differential mode parabolic equation. So it more or less, it was done by me and my co-authors, and now this, well, theory is more or less from the equations to numerics, and we developed it as far as like a general purpose numerical model, which is available on the internet, and more or less we offer it to everyone, and well, propose that people make computations and solve real problems using our software. So let me go further into the math. Well, we start actually the main thing, the main equation you start with is Helmholtz equation. Well, these Laurel indices stand for partial derivatives. So it's like Laplacian. Omega is angular frequency, and C is sound speed, and P is acoustic pressure. Well, and you normally have some point source. Well, as you have seen, not all acoustic sources are actually point. Yeah, they have, let's say size of few meters, but in comparison to the area, to the propagation area, they are quite small. So more or less, you can always use far field approximation, and you can always consider your sources as point sources. So for acoustics, it's no problem. So it's like absolutely normal. So we have a Helmholtz equation with a point source on the right-hand side. So in order to make a closed mathematical formulation, we also add a pressure release condition or soft wall condition at the sea surface. So acoustic pressure vanishes at the sea surface. We also have water bottom interface, and you need continuity conditions for acoustic pressure and for particle velocity, which is a normal derivative of acoustic pressure divided by the density rho, which is another important parameter. So we have two media parameters in acoustics: sound speed C and density rho. And we have continuity at this water bottom interface. And actually, this interface is what makes acoustics so much different from other areas of wave propagation. So we have an interface of very complicated geometry, and well, it poses numerous difficulties. And also we of course need a radiation condition at infinity. Well, let me overview the media parameters in acoustics. So normally you have sound speed, or we call it hydrology, because it's the information on the sound speed in the water column is obtained by hydrological measurements. When you deploy a hydrological probe, like it's a device, you put it into the water and it goes down and it measures temperature and salinity, different depths, and then you recalculate sound speed from temperature and salinity, and you get the information about the sound speed in the water column. And of course, if you want to do, let me go back a little bit. For example, here in this experiment, we made just 5 measurements of this sound speed. You see these dashed lines. It's well, it's locations of the on this path where the measurements were conducted. So you see, you can scarcely do more of them because well, you need to go along this path, which is quite long, and do the well, every time you have to deploy this probe, and you obtain the information, but everything changes very quickly. So if you do more of them, the situation changes, and you actually get the information about the environment, which is not the same where you did acoustic transmissions. So this is a complication of underwater acoustics. Sometimes you can get the information about the medium from the models of global circulation of ocean. You know, there are several models of global circulation from which you can retrieve this information. But of course, it's not the same as to obtain this information from measurements. It's always, you know, you never know exactly what this is, what is true in these models, what is not. So sometimes it works for you, but sometimes it's not, and you want to be more precise and do more measurements. But at the same time, measurements take time, and you see this is very difficult to find a, well, one-fits-all solution. So very often, if your path is not very long, like few kilometers, or maybe 10 of kilometers or 20 kilometers, you can expect that actually sound speed is almost range independent. It's almost independent on the horizontal variables. So you can only, you can assume that it's only depth dependent. Well, this is a, well, this, let's say, let us consider it as empirical fact, because in real ocean, well, it varies in horizontal directions much slower than in vertical directions. So you often can neglect these variations in horizontal variables. But at the same time, if you have a propagation path like of 100 kilometers, you can no longer neglect this variation. So you have to do something about obtaining information about hydrology, about sound speed, and its dependence on horizontal variables also. Well, typical values of sound speed in water, in saline water, is from 1,450 to 1,520 meters per second. This is a typical range where in which it varies. Sometimes this is for warmer water, like near the surface in summer. This is for colder water, which is more or less, let's say, near the bottom in summer, or near or more or less everywhere in winter. And you need also to know the bathymetry. Bathymetry, or bottom relief, is actually information well, on the variation of sea depths with horizontal variables. It's described by this function. And normally you more or less you have a variation of 1 meter on average per 100 or 200 meters in X and Y. So it's also in this sense, the marine environment varies in horizontal directions much slower than in vertical direction. And also you have sound speed in the bottom and density in the bottom and attenuation of acoustic waves in the bottom, which is measured in decibels per wavelength. And sometimes you want to include several layers of bottom into your model. And of course, in real seas, the layers of bottom are of also variable thickness. And so it's you can never get the complete information about the medium. So more or less you never have it. So sometimes you have to neglect something and you want to make your models as robust as possible to small inaccuracy in the media information. So what we start with what we call model decomposition. So we compute the eigenfunctions or modes of the, let's say, depth separated problem. So we separate the problem on vertical coordinate and we compute the modes, let's say, in a resonator between the bottom and the surface and maybe in water layers. So we compute these eigenfunctions by solving this spectral problem, and they are called normal modes. And they are, of course, you can normalize them. They are, let's say, orthonormal with respect to the following scalar product. And you can use them as a basis for the expansion of acoustic field. Let me just show you an example. So if we have, let's say, marine environment with depth-dependent sound speed, and then you have bottom at the depth of 60 meters, where the sound speed from jumps from 1,400 to 1,700. So then you have the normal modes of the following kind. So you have these are eigenfunctions of the modes. This is the first mode, the second mode, and so on. You see the frequency is 160 hertz. Well, and if your environment does not depend on horizontal variables, that is on X and Y, then your solution of your three-dimensional Helmholtz equation will be something like this. So you have mode functions in depth variable in Z, and you have Hankel functions in R. So I have some questions here. Good question. Where is the attenuation coefficient in the equation? Right. Let me go back a bit. In this equation, the attenuation coefficient comes as an imaginary part of the sound speed. So it's included here. So you have real part of the sound speed, which is more or less real sound speed. And then you have some imaginary part, which depends on this attenuation coefficient. Because the solution of Helmholtz equation is complex, so it's no problem. You obtain complex acoustic pressure. And if you want to go to the time domain, you more or less anyway do Fourier transform, and then you obtain the real time series. Yeah. So, but yeah, attenuation is included in the sound speed. But this solution, of course, is valid only if you have, let's say, you can do separation of variables. That is, nothing depends on X and Y. So then you have this one. And it looks something like that. So if I include only waterborne modes, so I don't include continuous spectrum, so then I'll have the interference pattern of this sort. So it's more or less the interference of these 5 modes, and the magnitude slightly decreases because of this factor square root of R in the denominator. So this is what you have if you have a range-independent medium. But if you have range-dependent medium, that is, if media properties, bathymetry, hydrology, if they depend on X and Y, then you can do what we call quasi-separation of variables. you can still use these mode functions as a basis for the expansion, and you can denote the coefficients of expansion, which are now depend on x and y, as aj, and we call them mode amplitudes. And if you substitute this expansion into the Helmholtz equation, into 3D Helmholtz equation, if you neglect coupling terms, I can later explain why you can neglect them, then you separate modes from each other, then you have the following equations of the following kind for the mode amplitudes. Well, these guys are called horizontal refraction equations. So they are two-dimensional Helmholtz equation instead of original three-dimensional Helmholtz equation. And now we would like to solve these ones. Well, and in many cases, if we solve these ones and then substitute this aj into this expansion and compute these modes and assemble this sound pressure from this sum, then you'll get sufficiently accurate representation of acoustic field. Well, for some examples shown below in the subsequent part of my presentation, I'll probably need curvilinear coordinates. So I would like to pass to the curvilinear coordinates. One example where we need that is when we would like to simulate the propagation along some curve. For example, such effect is important. It can take place when you have a set of curvilinear isobaths, and then you have something like whispering gallery formed near this family of curvilinear isobaths. So I just want to write this equation, rewrite this equation for mode amplitudes in these curvilinear coordinates. So let's say that isobath has the following parametric equation, and then I have the following transformation from this xy to new coordinates, which I call x and xi. And then I rewrite s and xi, and then I rewrite this horizontal refraction equation in these coordinates s and xi, where I have a parameter gamma, which is more or less something xi by kappa, and kappa is the isobath curvature. Well, curvature can be computed in the usual way from differential geometry. You probably all know this formula. Well, what I would like to do next is to write a one-way propagation equation instead of this Helmholtz equation in order to pass from Helmholtz equation for mode amplitudes to something like a parabolic equation. So first I make this change of variables in order to isolate the derivatives with respect to s, with respect to direction along this isobath. And then what I can do, if I rewrite this equation in this form, then I can separate propagation in one direction from the propagation in another direction. As I pointed out already, in underwater acoustics, you more or less can neglect backward propagation. So you can neglect backscattering most of the time, not always, but most of the time. I can explain when, if somebody will be willing to ask the question. So I can just formally factor this equation, and I'll have, let's say, factor square root from the operator on the left and square root from the operator on the right. And here I'll have the first derivative instead of second, which is clearly square root of the second derivative. And here I'll have a square root of operator L. So now I have one-way propagation equation. The problem is, instead of this differential equation, I have a pseudo-differential equation. The pseudo-differential equation contains a square root of a differential operator. This one is called pseudo-differential operator. But, well, I'll do another trick. I'll make another change of variables. This one, well, I would not like to go into details. It's a bit complicated. Well, not complicated, but probably difficult to explain like in 1 hour talk. So this one is necessary in order to obtain what we call energy conserving equation, in order to have energy conservation. So I rewrite out my one-way equation for this new variable phi, and it's here. But you see, this equation more or less has the same form as the previous one, so more or less you don't care. So again, it's pseudo-differential parabolic equation. And now what I do is I formally solve this equation in one step along the S direction. So I make a marching on the length of H. So then I'll have it in the following way. So I'll formally have this exponential of this operator. Well, here you see how X is related to L. So it's more or less the same as just make the propagator of this operator. And then what I'm going to do is to approximate this operator exponential by a Padet series. What I can do is approximate it with a Padet series. And then I can just formally apply this sum of operators to this to the function phi at some step in order to obtain function phi at the next step. And when applying this operator to the function phi, I more or less have to compute the inverse to this operator. And when I discretize it, I obtain, of course, something like inversion of a three-diagonal matrix. So it's quite simple, and actually. And well, for each step along the S direction, I need to compute all these terms, which are more or less inversion of several matrices. And then I compute the function phi at the next step. And I can do marching in range. And this is actually a very cool thing. This is a kind of what is called a split step Padet technique. And it brings you immense advantage because you can do stepping, marching in this direction, which is not directly related to the to your wavelengths. So you can do steps which are much larger than the wavelengths, like let's say 10 times larger than wavelengths, or maybe 20 times larger than wavelengths. I'll show you examples a little bit later. Well, what we need also, this is part of the game. If you want to solve it in Cartesian coordinates, you want to truncate domain in transverse direction somewhere. So you want to truncate so here it's written in Y, but actually, well, it should be psi here. So it's transverse variable. Well, you want to truncate it. If in order to truncate it, you can use two things. You can use PML, which is perfectly matched layer. So the layer on each side, which attenuates the waves which are incident on the boundary, and you have no back reflection from the boundary. So you can truncate your domain in this way. Or you can set up what is called transparent boundary conditions on these artificial boundaries, and then you can truncate it this way. Well, we actually developed both options, and we developed both transparent boundary conditions and PMLs for this case. So both work quite fine. But so sometimes one is better, some in other cases the other is better, but there are both options. Well, it's also not very easy to obtain, well, not, let's say it's not so complicated, but anyway, you need to solve this problem. Well, you have a boundary value problem for Helmholtz equation, and then you have boundary value problem for the mode amplitude, and you have the source on the right-hand side as an input term of this boundary value problem. But when you transform to the parabolic equation, you have initial value problem, or you have Cauchy problem. And if you want to solve Cauchy problem, you need some Cauchy data or some initial data, which somehow simulates your point source. And well, there are few starters known from usual parabolic equation theory. We tried them and we realized that they don't work for us. And we designed our own starter. So what we do is actually quite simple, but somehow nobody tried that before, and it's very efficient. You can just advance your solution a little bit using the race theory, and you start with delta function, then you advance it by race theory a little bit for some small distance from the source, maybe smaller than wavelengths. And then what you obtain using this race theory is your starter. Then you use it as a input data or Cauchy data. Here is some, well, I have another question. Okay, so Dmitry reminds that I have 15 minutes left. Okay, I'll try to speed up a little bit. So you have more or less different starters. And what is good about this our starter, which is shown here, is that actually the step size in this technique, in this method, depends on the starter. If your starter is not consistent with this parabolic equation, then you need to choose very small steps. But if your starter is chosen properly, then you can make large steps. So for the starters which are known from usual parabolic equation theory, well, you can do the steps of, let's say, a few meters for this example. But with our starter, you can make the steps which are as large as 500 meters or even 1 kilometer, which is very, very efficient if you would like to advance your field in hundreds of kilometers, right? Well, let me go further. And this is the last section of my talk, which is computational examples. So the first example is what is called coastal wedge. So the wedge with here's a coastline somewhere here, and you consider the propagation more or less along the line which is parallel to the coastline. And here you clearly have three-dimensional effect, so you can do it with a two-dimensional code. So this is if you your source is here, and this is if you consider the propagation in the plane, in this plane, then you have something like that. So the field will look like this. But if you, this is a vertical section, so you see this is Z and this is X. And if you do it in the plane, if you now want to do three-dimensional solution, and you have X and Y, and this is a horizontal cut plane of acoustic field, you have something like that. So this is a shallow part. So this is near the coast. This is a deeper part. So it's deep water, towards deep water. And you see that sound field is somehow refracted from shallow part to the deeper part. This is what we call horizontal refraction. So the effect when the sound field is moved from shallow parts to the deeper parts. So it's refracted. And you see, this is some reference solution obtained by something like source images. And this is wide angle mode parabolic equation. And this is the same wide angle, but with very large, well, for acoustics, for the very large step size. The frequency here is 25 hertz. So its wavelength is 60 meters. So this step is like 10 wavelengths, but you can also take 20 wavelengths, believe me. So you'll have you'll still have accurate solution, which is a big success for underwater acoustics, because normally you need several points per wavelength, but here you don't need it. I have one more question, sorry. Well, physical reason, depending on what you call physical. Let's say you can explain it in terms of rays, which do some reflections from the surface and from the bottom. And when if you consider how this ray moves in this wedge, you'll find out that, well, due to the nature of this reflection, it turned back. But also you can explain it on the model language. So your, let's say, so your horizontal refraction equation, so you have these wave numbers of the modes, which depend on these on the depths, and they form like something like effective refractive index. And the field is turned in accordance to this effective refractive index. So you just have these wave numbers working as a refractive index, just like a stratified medium, let's say. But again, it depends on what you call physical. Well, this is actually quite surprising for my friends working in underwater, in computational underwater acoustics, that you can actually, you can't obtain this using narrow angle mode parabolic equation, but with our pseudo differential mode parabolic equation, you can get the agreement with the reference solution, even not only along the x-axis, but also in cross sections, which are, let's say, parallel to the bottom slope. This is very surprising actually, but maybe not for the people which are not working in acoustics.
Pavel, sorry, there is another question.
Yeah, got it. Several approximations. How do you control the accuracy? This is a good question. So, well, let's say we have several benchmark examples, and we tested in these benchmark examples and compare the results with other methods like here. But of course, and also you more or less know when you can neglect this one and this one. For example, two main things we neglect here are: one is backscattering, which more or less, if you have a penetrable bottom of the slope and the slope angle is like below, let's say 1 or 2 degrees, then you more or less can neglect backscattering more or less every time. And let's say on the in shallow sea, on the continental shelf, you have slope angles. Typical slope angle is about, let's say, 0 point something degrees. So the slope angles are very small. So that's why you can neglect, more or less neglect backscattering. The other thing is mode coupling. It's a bit more difficult, but let's say in many cases you can neglect mode coupling. And if you, let's say, at every point you will have some mode coupling somewhere at some frequency, but you will not have it for most frequencies. That's why if you stay in shallow water, you can more or less all the time neglect mode coupling. But of course, yes, you have to understand physics. You have to understand where this effect will come into play. But let's say in many cases this is good. Yeah. And also you have to keep in mind that this is underwater acoustics. So sometimes you don't need accuracy of several percent because your measurements are taken, let's say, with accuracy of 2 to 3 decibels. So you don't need accuracy of 2% or 5%. You're okay if you have accuracy of 10%. But you have to produce it. You want to have your results to be robust, reliable, and more or less, well, if you have an accuracy of 10%, sometimes it's no problem, right? Another example is underwater canyon. Well, what you have is focusing above the canyon. So if you put the source above the canyon, then you have acoustic field focused in the canyon. So large part of acoustical energy will be ducted in the water column over the canyon and will propagate along the canyon like it's some fluid or something like that. But it's acoustic energy, but it still feels these variations of bottom. So this is our solution, and this is a reference solution obtained using so-called virtual sources technique. And in this case, you have strong mode coupling, and you can see that there are tiny features which are different from what you obtain with parabolic equations. But these tiny features, you don't need them when you actually want to do sound level estimates in underwater acoustics. So you are okay with these small differences, but they do exist and they result from mode coupling. So they are here. My point is they are here, but you can neglect them if you're okay with this typical accuracy, let's say. And if you compare, you'll see, yes, they're here. The small differences are here, but more or less you have accurate prediction of the field levels. And one last example is what I call whispering gallery. So if you have several isobaths, if you have some area of the sea with a bottom which has a shape of a bowl, so you have isobaths which are arcs of a circle. So you have a slope, and the slope is a bit curved. Then you can have an effect if you place the source over this area. You can have an effect which is which I call whispering gallery. And in fact, it looks like this one. So you have some acoustic energy which will be trapped near this isobath. Also, this is not canyon, this is not a real duct, but it works in the same way as normal whispering gallery in a cylindrical building. But in the cylindrical building, the physical effect beyond the whispering gallery is numerous reflection from the wall. But here, the physics of this effect is horizontal refraction. And you have horizontal refraction as a mechanism of whispering gallery formation. This is quite interesting. We found it, well, we were first to describe this effect with my colleague from Israel. And another, the last probably slide with a figure. Well, if you have a whispering gallery formed near these two isobaths, you see this is an isobath of 24 meters. This is an isobath of 26 meters. So it's like a very small slope of 2 meters. And at some point, if you have an inflection point of this isobath, so at this point, the whispering gallery will disintegrate and the acoustic energy will be radiated in the form of what is called searchlight beam. So, and if you solve this mode parabolic equation in these curvilinear coordinates associated with this isobath, then you have this effect, which is not really easy to obtain by other methods. Okay, so this concludes my talk, and thank you very much for your attention, my friends, and I'd be glad to answer further questions if there are any.
Okay, thank you, Pavel, for the interesting talk. Dear colleagues, do you have any questions? Please ask him and tell your name and other question. Alexey, I see your hand.
Yeah. Thank you very much, Pavel. Very interesting. Very difficult to understand, but very interesting. So the question is the following. So in the simulation, when you calculate for the case, for example, for the canyon, I believe this is quite feasible to do in the, let's say, experimental condition to produce such a setup and to reproduce at least part of your figure, let's say, to make a huge swimming pool and to do this measurement. My question is, are there any groups in the world who are doing such experiments? Let's say, I understand that in the ocean, everything is changing this time, but like within the pool, you can control everything and you can do measurements and compare it with your theory. Thank you.
Yeah, correct, Alexey. Thank you for a very nice question. Yeah, there is an area of what is called tank acoustics. So you can do experiments not in the real sea, but in tank, in some reservoir with water, not combat tank, I mean. Wow. And people do reproduce this kind of environment. They can do they do it in several ways. Some of them just put the sand like with a slope, like in the wedge, and they do measurements and they do comparison with measurements and computations. Yeah. Some other people, they print the shape of the bottom using some porous material using 3D printer, and they produce something like canyon, and they first they do measurements and they do simulation, and they even do what is called scale model experiments. So for example, if you have, let's say, some real canyon in the ocean, so you can just decrease its size by, let's say, by a factor of 10 to the power of 5, let's say, and you can decrease your frequency, sound frequency accordingly. So instead of acoustic frequency typical for underwater acoustics, you have, and let's say something like ultrasonic frequency, and you can do scale model of this, what happens in the ocean. So this is actually another topic, and some people are doing that. Some people in France, like in the University of Marseille, and some people in the US, like, for example, in the University of Texas. So yes, there is this field, and yeah, but unfortunately in our institution we don't have a tank for such experiments. So.
But did you try to, for example, to reproduce some experiments by your numerical model or something like this, or it was?
Yeah, sure. So, but not tank experiments, but real sea experiments. Yeah. So we reproduced a lot of things. For example, well, the one thing, well, people who are doing this acoustic navigation, and they at some point they had inaccuracy more than they expected, and they addressed us if we can explain it, and the explanation come from the taking this horizontal refraction into account, which produce you few additional hundreds of meters. Yeah, and so we collaborate with the people who are doing experiments all the time, more or less.
I see. Thank you.
Thank you for the question.
Okay.
So I have another question from the chat. Does your method work with a regular grid? Probably it does, but we never, to be honest, we never tried that. So we always worked with regular grid. First thing is that we always wanted to be robust. So maybe sometimes it can be an advantage, especially near the source, when you probably can you can probably use finer grid, and it can be an advantage, but we actually never tried.
Okay, dear colleagues, if anybody has a question, raise your hands. Okay, actually, I have a question. So in the first part of your talk, you told about the noise level and how to measure it, as I remember. So may I ask you, what is the noise level? Because in the ocean, everything changes, as Alex told and as you told. And yeah, first of all.
Right. So noise level, well, when you study impact of the noise on the marine mammals, for example, or other animals, the quantity you are interested in is a so-called sound exposure level, or SEL. This sound exposure level is a, let's say, integral of acoustic pressure squared over the time and over some time interval, let's say 1 second. And you want this sound exposure level not to exceed some value, which is some reference value, which is known from the study of these animals. So they are, let's say, they become anxious when the sound exposure level exceeds some this threshold. Yeah, and this is what you actually compute. And you can also measure this quantity. You can just put the hydrophone, you can take the measurement of this over this interval, integrate and this time series, and then over this interval, and you have this experimental quantity, sound exposure level. But you also, the purpose of modeling is to compute sound exposure level of some over some area. Yeah, so but it's always measured in decibels, because there is always some reference value, let's say some kind of micropascal squared times 1 second, let's say, and you always compute everything in decibels with respect to this reference level. So did I answer your question, or?
Yeah, I think yes. So the second question is, at what frequency you work?
Wow, okay, this is very good question. Right. So, well, we normally, right, if you have higher frequency, you always have better resolution, whatever you would like to resolve. But at the same time, when you have higher frequency, you have larger absorption rate in the seawater. So normally acoustics, the area of acoustics I work with, this is a few hundred hertz. So for example, navigation sources, they are, let's say, 300 to 500 hertz. When you study noise level, you are more or less concerned with frequencies from, let's say, 20 hertz to, let's say, 200 hertz. When you want to study well, when you are concerned with the impact on the marine mammals, you are concerned with the frequencies these marine mammals can recognize. For example, sperm whales can recognize frequencies from 10 hertz, which is below the human, let's say, hearing threshold, allow, and to 40 kilohertz, if I remember it correctly. Well, but you see, when you work with some high frequency noise, it can propagate large distances.